Welcome back to my channel. Today, we're diving into an exciting topic, signal processing using MATLAB. This is a quick overview of the signal processing Onramp course. Let's break it down. 1. Course overview. The course introduces the fundamentals of signal processing and its real-world applications, using MATLAB and the signal processing toolbox. It focuses on vibration signals from seismic stations in Alaska and helps you identify an earthquake signal from a distant event. Introduction to signals. You'll explore how signal processing techniques help in analyzing, modifying, and extracting information from signals. Real-world examples are used, such as how cars use signals from radios, sensors, and GPS systems. MATLAB basics. While you don't need advanced knowledge of MATLAB, basic familiarity is required. If you're new to MATLAB, the course suggests starting with MATLAB Onramp to get up to speed. Tools. Throughout the course, you'll use a web-based version of MATLAB for hands-on learning, but the language and functionality are the same as MATLAB's desktop version. Key tasks. Generate signals. Set a sample rate of 100 Hz. Create a signal vector with time steps of 1 by fs. Create a 5 Hz sine signal and plot it. Generate random noise and add it to the sine signal. Then plot the noisy signal. Create a 5 Hz square signal and plot it for comparison. 2. Signal data in MATLAB. This module focuses on real-world signal processing using seismic data from the 2004 Sumatra earthquake. You'll work with data collected by seismic stations in Alaska, using MATLAB to analyze and visualize the signals. Seismic waves. Earthquakes produce seismic waves that travel through the Earth's crust, which can be detected by seismometers. This module explains how seismic signals can be analyzed to study earthquake behavior. Signal processing workflow. The course walks you through the standard workflow. Import the seismic signals into MATLAB. Preprocess the data to prepare it for analysis. Visualize the signals in both time and frequency domains. Use filtering techniques to isolate key frequencies. Extract useful information from the signals, such as timestamping tremors. Key tasks. Import and plot signals. Import a seismic signal from the harp.csv file and store it in a vector named harp. Plot the signal to visualize it. Use a timetable to associate time information with the data and work with the signal more easily. Signal Analyzer. Use the Signal Analyzer app to visualize signals and explore them in both time and frequency domains. Display the power spectrum of the signals and zoom in on regions of interest using panning tools. Export processed signals to the MATLAB workspace for further analysis. Compare signals. Import multiple signals, align their sample rates, and compare their power spectra. Focus on filtering and extracting important features. 3. Pre-processing signals. This section covers key pre-processing techniques to prepare real-world signals, which are often noisy or non-uniformly sampled, for further analysis. Challenges with real data. Sensors can introduce imperfections into data, so pre-processing is essential. You'll learn to resample, align, and clean up signals before analysis. Resampling signals. If signals are sampled at different rates, you'll learn to upsample or downsample them to a uniform rate. Upsampling. Interpolating signals to match a faster sample rate. Downsampling. Reducing the sample rate, which discards high-frequency information. Noise removal. You'll apply filtering techniques to remove noise or irrelevant patterns from signals, ensuring cleaner data for analysis. Key tasks. Resample signals. Resample the pack signal to match a uniform sample rate of 50 Hz and compare it with the original signal. Downsample the wonk signal by a factor of 0.5 and display the impact of resampling. Extract regions of interest. Use tools to zoom in on specific portions of the signals, 15 to 30 minutes, and extract them for closer analysis. Custom pre-processing functions. You'll learn to apply custom functions to signals, such as converting units from nanometers to centimeters, and display the results. Signal alignment. Align multiple signals, e.g., harp, pax, and wonk, to ensure they're synchronized for comparison. 4. Spectral analysis. A. Frequency analysis. Time domain signals may look different due to varying frequency content. Mount Wrangel's signal differs from HARP and PX because it contains high-frequency content. Using Fourier transforms, signals are decomposed into their frequency components. Power spectrum plots help analyze the intensity of each frequency. Low-frequency content is similar across all stations, but the Wrangel station records additional high frequencies from local earthquakes. B. Customize power spectrum plot. Task: display power spectra of all three signals and set the frequency scale to log. Comparison: HARP and PX have similar low-frequency content, while Wrangel contains high-frequency components. C. Time frequency analysis. Power spectrum shows the overall frequency content, but time frequency analysis reveals when these frequencies occur. Methods: spectrogram, based on sine waves. Scaleogram, based on wavelets. Both methods slice signals into blocks to visualize frequency changes over time. D. Create time frequency plots. Tasks: create a spectrogram of the Wrangel signal. Set the frequency range from 2 Hz to 10 Hz and the power limits. Create a scaleogram and compare both visualizations. Determine which method better identifies local earthquakes. 5. Filtering. A. Filtering video. High-frequency components in Wrangel make time domain comparison difficult. Use a low-pass filter to focus on low-frequency content for better comparison across stations. MATLAB can design filters automatically or based on user-defined parameters, such as passband frequency and steepness. Trade-offs in filtering. Higher steepness gives narrower transition bands but introduces more artifacts. B. Low-pass filter. Tasks: apply a low-pass filter to the Wrangel signal and compare its power spectrum with the original. Compare HARP, PX, and filtered Wrangel signals in time and frequency domains. Test different steepness values to observe filtering effects. C. Bandpass filter. Tasks: create a bandpass filter on Wrangel between 2 to 10 Hz and compare it to the original. Compare the filtered signals in the time domain between 3 to 5 minutes. Observation: high-frequency pulses correlate with peaks in low-frequency content, indicating local earthquakes triggered by the original Indonesian earthquake. 6. Signal measurements. A. View generated code. In Signal Analyzer, you can extract measurements from time domain and frequency domain signals. Exported code allows for customization and replication of pre-processing and visualization steps. Use scripts to recreate a spectrogram or filter signals. B. Signal measurements tasks. Tasks: modify the spectrogram code to add output arguments. Calculate the sum and power of the spectrogram, plotting them over time. Use the Find Local Extrema task to detect earthquake timestamps based on the power plot. So that's a quick overview of the Signal Processing Onramp course. We covered the course introduction, working with signal data in MATLAB, how to pre-process signals, spectral analysis, filtering, and signal measurements. Stay tuned for more videos where we'll dive deeper into each topic. If you found this helpful, hit that like button and subscribe for more tech content. Meet you in next video. Thank you. Bye.